This is part 2 of section 2.2. We're going to talk about increasing and decreasing functions. Here are our formal definitions. They may not make too much sense to you, but I always give you formal definitions and then explain them. A function is increasing on an open interval I if for any x1 and x2 in the interval where x1 is less than x2, then f of x1 is less than f of x2. Okay, what does this mean? So we have some sort of graph, and our x values, x1 is smaller than x2. So let's say this is x1 and this is x2. And we have some sort of graph. Now, my graph at x1 is right here. My graph at x2 is up here. Now, what y value does this correlate with? Well, whatever it is when we plugged in x1. So right here on the y-axis, this would be f of x1. And then right here on the y-axis, I think I said x earlier, but it should be y. This is what we got when we plugged in x2. Okay, so if your x1 is less than x2, then your y values, which is what means here, when you plugged in x1, you got a smaller value, and then x2, you got a bigger value. That's all. And when you look at the graph, it looks like it's going up and from left to right. We're always looking from left to right. Okay? Now, a function is decreasing on an open interval for x1 and x2. Notice my x1 is still smaller than my x2. But here, when I plug in x1, it needs to be bigger than x2. And basically, what this graph is going to look like is something like this. When you look at it from left to right, it's going down. And it's constant if you always get the same answer. And a constant is going to look like this. It's going to be horizontal. Okay? Now we say open intervals, and that's because when we're talking about where something is increasing or decreasing, you don't include, so let's say this is increasing and then all of a sudden it starts going down. Right here where it changes directions, you can't say whether at that one point if it's increasing or decreasing because it changes there. So that means we're always going to use parentheses. We're never going to include our endpoints, okay? And when you're asked to do this, so we're going to use this graph to determine the intervals where the function is increasing, decreasing, or constant. Now, when you're asked where something happens, we're looking for the x values. We use our x values to determine basically the location. If I'm looking on my graph, where does this happen? Okay, so where is this increasing, decreasing, and constant? Okay, so let's look at this. Where's my graph going up? Well, it starts off down here, and it's going up all the way to right here, correct? So this whole region, so it starts off at negative infinity, because this is going down. We tend to think of it more down, but our x values are always going to infinity. So that's a stray mark there. So let's mark this back out. So negative infinity, comma. Where does it stop increasing? Well, it stops increasing right here, correct? What x value does that correlate with? -1. Okay, so where on the x value is it increasing? All the way from negative infinity up to -1. Okay, where is this decreasing? When I glance at my graph going from left to right, does it ever go down? And the answer is no. So this goes nowhere. It's nowhere decreasing. Where is this thing constant? Well, once it stops going up, it goes flat. So this is constant here, and it goes off to infinity. So remember, we're talking about x values. Where is it constant on the x? Well, it's constant from -1, remember to use parentheses, to infinity. This type of problem, if I could give you this problem and just have you show me on the graph where it is, then this would be very easy. The hard part is remembering how to write it down. Okay, so let's do another one of these with this graph. Okay, so I do go off to infinity in both directions. Okay, so where is this thing increasing? Okay, it is flat here, it's flat here, and even though it changes directions, it's still going down this whole area, right? So it's increasing nowhere. This thing is never going up. Where is it decreasing? Well, even though it changes directions, it's decreasing from here to here. Now, where are these on the x-axis? Okay, it's decreasing from 2, 3, 4, -4, all the way up to here, which is +2. So on this interval, this x interval, we are decreasing from -4 to 2. Now, where are we constant? We're constant in two different areas, and that means we're going to have to write these two interval notations separately. Well, this goes off to -infinity. And then where does it stop? It stops being constant at -4. Okay, so that's this interval. And then we also have this interval, which starts at +2, and it goes up to +infinity. Well, since it's both of these, we use a union between them, and we have our answer. Okay, new definition. A function value f of a is a relative maximum of f if there exists an open interval about a such that f of a is greater than f of x for all x in the open interval. So basically, if I have a graph like this, I have a maximum right here, because if I consider the x values here to here, a small interval around it, this number is bigger than everything else. That's all this is saying. This one, if it's smaller than everything else, you have a relative minimum. Okay. So we're going to use the graph to identify relative maxima and minima. Maximum, minimum, these are plural versions of those words, if they have any. Okay, the way these problems are worded, okay, the numbers, if any, at which f has a relative max, what are these relative maxima? Okay, and then basically the wording is repeated except for minima. Okay, you're going to be asked where it happens, and this is your x value. And then what is the value? What is the maxima? This is your y value. Okay, so let's just look at this. This goes up forever, this goes up forever, but right here, that point is higher than everything else in its area. This is a relative maximum. So where does this happen? This is your x value. This point right here is the point 0, 1, 2, 3, 4. So where does this happen? At 0. What is the maximum value? 4. Okay? Or you can think of this, and this is equal to f of 0. Okay? Now we're going to do the same thing for relative minima. Okay? And here we have 2 points that are smaller than everything else in its general area. It's lower down. And that would be right here and right here. So let's think of what these 2 points are. This is the point that would be -2, 0. And this is the point 3, 0. Okay? So for this one, if we're asked where, I have a relative minima at -2, and I have one also at 3. Okay? The online, it's going to ask you to do it like this. It's going to say, where is it happening? And you're just going to plug it in right there. Okay, and then they're going to ask, what are these maximum values? Okay, now it just so happens that both of these are 0, so you would only need to list it once, but it is possible that this one's here and then your other minimum is down here, and so you would have different values here. But this is how this works. Okay, so we're going to do one more of these. Okay, so let's find relative maximum and minimum. Okay, so do we have a maximum? Do we have something that's higher than everything else in its general area? And the answer is yes, it's right here. That would be our relative maximum because it's higher than everything else. So where does this happen? Where is this on your x-axis? Well, what point is this? It's 0, 2. So where does it happen? 0. What is the maximum value? 2. Okay? Now let's look for relative minimum. If you look at this, I had some trouble getting this drawn on the computer, but it's pretty good. You can see that I intend for this to change directions right here. I have arrows on these indicating they continue forever. But right here, it changes directions and it will be lower than everything else in its general area. And then the same thing happens right here. Well, this point would be, that's -3, -1. And this is 3, -1. So where do we have minimum? We have one at -3, and we have one at positive 3. What is the value? The value? -1 and -1. So we only need to list that once.